At some point, you've probably either thought about or tried and failed to use a screw in a 3D print, or worse, you've not thought about it at all and you've been relying on heat inserts or glue or whatever instead. I was the second one actually, and now I feel stupid. Let's go. This video is sponsored by PCBWay. My aim in this video is not to prove what follows is somehow better than the other solutions I've just mentioned. My aim is to actually present alternatives to existing common practices in the 3D printing community and to try to make a case for those overlooked options, namely screws, that in many situations are the right option, for the reasons I will go over at the end. I have a life-size machine screw in my hand here, I just happen to have really small hands. The point I want to get across here is that we're not talking about these screws in this video. These are standard machine screws, in this case a scaled up M3 machine screw, with actual M3 screws being obviously much smaller, 3mm to be precise. What I want to talk about in this video is these screws, and I hope at this scale you can see the difference being primarily the threads. What these are is plastic screws, not screws made out of plastic. These ones are, but plastic screws made out of plastic is a thing, and unfortunately that makes it quite hard to search for screws for plastic. These screws are specifically designed to be used on plastic, but they're not plastic. They're usually sold as self-tapping, although that's not quite always the case, as we'll see. They differ from normal self-tapping screws in around two ways. Firstly, they don't have a point usually. I mean, at the tip, not like these big ones that also don't actually have a point. It turns out you can't scale up a screw and expect it to work. If it's not immediately obvious what a 30-degree thread is referring to, it's this angle here. The reason they have these 30-degree threads and not the usual 60-degree threads is because it suits plastic better. I've got some inverse threads here made by just cutting the screw out using modifiers in the slicer. This isn't in any way how you make functional threads at all, so it's no surprise that they don't work. The thread on the machine screw is very much nothing at all, though you can see that, and you would be surprised if it withstands being pulled out in any fashion. There are two distinct types of screws for plastic, and most if not all fall into one of the two categories, that being thread cutting and thread rolling. The first one does as you might imagine, it taps or cuts the thread into the plastic as you put it in. This is a destructive process and it absolutely will wear on repeat insertions, and it does remove material. But while it cuts a clean path through the plastic, the generally more common and arguably better screws for non-brittle plastics, which is most of the plastics that we use in 3D printing, are the ones called thread rolling, or sometimes called thread forming. These are designed supposedly to form a thread by effectively pushing the plastic aside rather than cutting it. For the video, I've sourced a selection of reasonably equivalent screws from various places. Some are cheap ones from eBay, some are better quality ones from Amazon, that are more specialist or claim to be, and then some are from Accu, which is a website in the UK who do ship internationally, and their screw range is, to put it mildly, vast. They also kindly gave me permission to use their CAD models for this video, that's what I was showing you a minute ago. Within the subcategory of thread rolling plastic screws, there are also numerous features that stand out depending on which screw you go for. Features including a bulge in the middle that serves the purpose of balancing out internal stresses, and the intriguing Trilobular screw that I sourced from two places. Trilobular screws, I presume I'm pronouncing it correctly, they have a triangular profile, but it's almost indistinguishable to the naked eye unless you look very, very closely. Thread pitch, which is the distance between the threads, tends to be a lot higher on these kind of screws than other screws, as you can pretty much see. And the thread angle I already mentioned is normally 30 degrees, but on some of the Trilobular screws it seems to be 45 degrees. These features are all very intentionally engineered for plastics like the ones we use in 3D printing. It's generally the same plastics as you use in injection moulding that these screws were designed for. It's probably no surprise, but it's not all about the screw. At the extreme, you can try and make a hole that's too big or too small for the screw, and it will either fail or be impossible to use. So one could argue that the hole is equally as important as the screw. For most plastics, the pilot hole should be roughly 80%-ish of the screw's major diameter. That's the overall diameter of the screw, the 3.5 in the M3.5, for example. If that hole is too small, then the displacement of the material, especially in thread-forming screws, will split the layers of the print. Too big and you're sacrificing grip, but also, well, hold that thought. Watch what happens on the thermal camera when I drive one of these screws into a pilot hole. The surface temperature you're seeing peaks about 40 degrees C, give or take, but that's conducted through the plastic, so the actual temperature at the cutting tip is higher. Work through the maths, I don't really want to personally, but you will get to potentially instantaneous temperatures of around 80 degrees C or above, which for PLA is above the glass transition temperature, and that's the same for quite a lot of plastics. I can't prove what's happening at that interface between the threads and the plastic, but here's what I can say. None of the samples showed any stress-based fractures. What I think, and this is a think, is that heat is allowing the plastic to flow into the threads rather than fracture under stress. There might also be some localized stress relaxation at the interface, and this is down to the heat that's being generated by the screw. The possible glazing effects that I observed could be consistent with this, or it could just be an artifact of the way I'm looking into the screw thread. And this, logically, is also why pilot hole size matters more than you might expect. The right fit gives you optimal friction, which maximizes this effect. It's worth noting that the example for the thermal imaging is PLA, which has a relatively low glass transition. Whether this applies to other materials is an open question. I suspect it does, but it won't be universal. But back to hole size, and it gets a bit muddy when we're 3D printing because there's a very good, almost 100% chance that your hole will not be the size that you think it is. The problem is that no matter what order you print the walls of a part in, whether you do outer wall first, outer wall second, the inner hole of a screw hole is always unconstrained, so there is always a tendency to some extent for the materials to spill into the void or just not create an accurate hole for a lot of reasons. I don't think it's worth trying to stop that with slicer settings, but instead you can calibrate for it. The ideal hole, you can look this up. For example, if you buy your screws from somewhere like Accu, then it's very easy because they provide you a list of values. For a 3.5mm screw, that's somewhere around or just about smaller than 3mm, and that kind of works for FDM in my experiments, which we'll get onto. The best way of actually checking is to print a hole that you think is, say, 3mm, and if you don't want to spend money buying a gauge, because they're quite expensive, just get a drill bit and use it as a cheap fit check. But bear in mind that drill bits aren't actually always close to the size that you think. For example, the drill bit here, I did measure it with the micrometer screw gauge. It's actually 2.95mm in reality, not 3. It might seem like a small difference, but actually when you're talking about screws, it's not that small. So the process would be measure your drill bit, see if your drill bit fits, and then calibrate for that and work out a factor. And then you should get a hole about the size that you are expecting. In my samples that I printed horizontally with the holes facing down, a 3.2mm hole in the CAD drawing turned out to be about 2.95mm in reality, which just happens to be perfect for a very tight fit for PLA with an M3.5 screw. But I also tested around those values to see the actual marks of the thread. This will vary slightly by screw, of course, but hopefully in a moment you'll discover why you have a reasonable margin of error here. So whilst everything I've just said is saying that you need to be very accurate about your measurements, it's actually not that critical in most use cases. I'll show you a tool I've made to get the holes right first time, but before we continue, I want to show you this cool PCB I've made using today's sponsor, which is PCBWay. With PCBWay's help, you can design your own PCBs, export the Gerber files, people have been telling me it's pronounced Gerber, I don't care, and upload those files straight to PCBWay's website, where they will take care of the rest. You'll shortly get hold of the PCBs, and you'll be able to continue with your project. The turnaround time can be crazy fast in my experience. If you need PCBs made, or if you need anything else like functional 3D printed parts in materials such as nylon, anything like that, CNC parts, sheet metal, and a lot more, you can get it all made at PCBWay. All the information you need, including material-specific information, is all there on their website. So check it out in the links in the description, where there is, as always, a new user discount coupon. Thank you, PCBWay, for sponsoring this episode. Now back to, holes. So I thought we kind of had a missing link in this video. It's all very well telling you to use 80% of the major diameter of the screw, but that's kind of hard to figure out and remember. It's kind of effort, so I decided to make this tool. I'll link it below. It's pretty easy to use. You select the material that you're screwing into and the screw size that you've bought, choose what level of engagement you want. No reason not to leave it as standard unless you want more engagement, which would be create a stronger but potentially more chance of failing, if that makes sense. And then you decide if you want hole size compensation, which is what we were just talking about. You generally will want to turn that on for FDM, but you'll have to do the calibration, and you only really need to use it, I think, if you're aligning the hole with the Z-axis. meaning perpendicular to the bed, because if the holes are on X or Y on the side of the part, those axes aren't generally as affected. Your mileage may vary. Print calibration parts, I'll provide those. Then the big number that the page spits out will be the size that you need to design your holes in CAD or in the slicer or whatever. I found it very useful. It's free, obviously. I'll link it in the description. Go and have a play. I ran a lot of tests. I think I spent about £150 on screws, and I really messed up my arms doing this. So please subscribe. I don't know how that helps, but it feels like the right thing to say. The tests generally fell into two categories. The first being tests to try to split the plastic and find the limits. The second being the more comprehensive tests based on torque, including both the torque used to insert the screw in the first place, which, by the way, is not linear, so I kind of had to figure out what the average was, and the torque required to cause a failure, which is precise, because I have this torque screwdriver here, which gives me exactly that. It will give me the max torque when I screw the screw in before it fails, and the failures aren't actually always the same, but the overwhelmingly more common failure is the screw starts spinning in the hole, which is interesting. The reason I ran these specific tests is beyond the scope of a brief explanation, but I will issue one nonetheless. It's attempting to replicate meaningful and common failure modes in an easily testable way, and this is a common proxy to that. And these are kind of industry standard tests, or a version thereof. Before we go into the results, I want you to understand something very clearly. All the tests converge on a single solid narrative. And that narrative is that for the vast majority of uses where you do not wish to repeatedly insert the screws, meaning more than, say, 10, 20 times, there are indications of solid advantages to using these specific plastic screws instead of other methods. So the easiest to start with is the edge testing, and this was very surprising to me. I did think that a printed part, printed flat on the print bed, with the screw holes oriented in Z would be strong enough because you're going perpendicular to the grain, if that makes sense. It shouldn't split. What I didn't expect is that it's nearly impossible to split the part, even making the holes like ridiculously proximal to the edge, way further than you would in any kind of sensible design. This isn't really that big a failure mode. You do get some marks on the edge of the part, but you shouldn't do this in case it isn't already clear why. You can see those stress marks there on the outside of the part in the closest to the edge example. While it may not fail immediately, it probably will over time. PLA and some other plastics are very prone to creep, and so they will just take their time to fail. What I really didn't expect, though, was that this performance would be almost nearly indifferent in most cases, regardless of orientation. Testing using normal PLA, none of the orientations of the print failed within reasonable limits, and the same for the other materials that I tested. So there's a reasonable assumption that unless you're printing with known weak filament that has terrible layer bonding, for example silk PLA, which I didn't test because it's so terrible, why would you ever try and use it for a functional part? Don't do that. But otherwise, you don't necessarily need to be too concerned with orientation when you're printing screw holes. If you do suffer from splits when you're putting screws in, it's far more likely to be a failure in printing than in the actual design. And this is pure speculation, but you might find that older printers don't have as good layer adhesion as newer ones. I've been testing on the Core one and the new Elegoo Centauri Carbon, and they seem to be fine. The second one I'll be reviewing next video, by the way. So drive torque and strip torque are the two methods I mentioned earlier, and you can see the results on screen. There's a lot of results, so I'll just kind of put them through as I'm talking over them. Picking out the story here was quite a challenge because there's a lot of things you could say. Ideally, you want the difference between the drive and strip torque to be about 3 times or more, and in my tests, most, if not all, of the samples actually achieved that. PLA works the best, but we do have to be mindful that nothing happens in isolation. PLA is subject to creep, so the application is important. The screws probably still won't be what fails on a PLA part, though, if you use one functionally. So my advice would be to choose the material for the application and just trust the screws. The ideal number of walls is probably material dependent, but I recommend 4. 3 might work, but there's not a huge case for it. You can use modifiers in most cases if you want the holes to be 4 walls and the rest of the part to be different. Saves material, doesn't sacrifice strength. Infill type and density probably does matter, but I couldn't really replicate it in tests. Lack of infill is probably more likely to cause a boss to split, but this only happens at abnormal torques or with materials with very poor layer adhesion. And this is probably more important a consideration for parts you expect to be under strain. Longer screws, unsurprisingly, work better. This is supported by common sense, science, and the tests. Cheaper screws don't perform as well as the more sophisticated ones, and the price is not hugely different for a low volume application either. If you only need, say, 6 or 10 or 20 screws, it's worth spending a bit more on trilobular screws if possible. In fact, both trilobular samples had much higher safety margin, that's the difference between the two torques, than any other screws. So I would be confident that while you can't see with the naked eye which are trilobular screws, if you gave me a box of mixed screws, I could figure out which are trilobular just by feeling how they go into the hole, because you can really tell even by hand. And I think related to that, one of the questions that I would have watching this video is how well can you tell when you've hit the max torque? What's the chance of you actually over torquing these screws and splitting the thread? Well, in my experience, you just know. When you've reached the end of travel, you feel the head butting up against the piece, and you can tell that that's when you should stop. That's the point of the safety margin. And related to that, there's a line of thought that you should insert a machine screw and that would be fine. For that exact reason, I beg to differ. When you blow up a machine screw and its prospective formed thread, you can see why. The machine screw is designed, obviously, for a receiving nut. No matter what you do to prepare the hole, whether you change the design of the internals of the hole, whatever you do, you're still going to face the same fundamental problem. The threads are just not penetrating the plastic enough. And given all that we've talked about, it's no surprise when you see this graph. This is where you see what could be referred to as a poor safety margin, to put it mildly. There's barely any difference between the torque needed to screw this screw in and the torque needed for the screw to start slipping. It's just not worth trying to use machine screws, in my opinion, if you don't have a captive nut and a design for that. If machine screws are the only screws you have, then, in my opinion, you'd be almost as well just hammering it in. It might work better. Who knows? I didn't test that. I didn't spend a lot of time testing heat inserts either, because this video is not about those. It would be an entirely different video, and plenty of those already exists. Heat inserts, as we know, generally provide the highest repeatability and pull-out strength. Heat inserts are what you use when you want repeatability, a lot of repeatability, but they aren't the only option, of course. Heat inserts are what you use when you want repeatability, a lot of repeatability, but they aren't the only option, of course. You can get these things. They're essentially screw threads with a screw thread inside, and they are slightly more convenient because you could still make a hole, you don't have to heat anything, you screw this thing in, and then you've still got that repeatability. But these are oddly expensive, and that's probably why nobody's using them. And then there's also captive nuts, which are really popular on Prusa machines. They use them all the time, and they are excellent at this application if you want repeatability and strength. If you do want an episode on either of these, then comment below and I'll fit something in when I can. I'm probably going to do one on captive nuts anyway. Anyway, going back to the data, one anomalous, or maybe not, piece of data that I found was comparing between a Boss test part and a test block. I was able to achieve much higher strip torques on the block. I don't think it matters from a design perspective because I don't think you're really supposed to be inserting the screws at this kind of level of torque, but I think that the reason why the discrepancy in my results are because of this effect. CF and GF filaments do potentially work, but probably aren't necessary if you're just thinking about screws. But if you're using them anyway for another application, then you are likely to see a slightly higher maximum torque compared to the non-CF or non-GF. There are some weird exceptions to this because some filaments become brittle when you add these things in, but I suggest if you're planning to use any filled filament of any sort or any kind of exotic filament, then there's an easy way to find out. I will share my files, or you can create a test piece yourself. It's not that hard. It's better to find out the filament has 0 layer bonding strength and your screws are going to split it before you actually print the whole thing. So a test part is kind of part of the process, I think. I think this is a win for specialist plastic screws whichever way you slice this. Literally. What I found in this video is that screw performance in 3D prints is not that distant from how it would be in injection moulded parts, at least on modern printers. Layer adhesion and plastics have probably improved a lot, as has slicing, and probably also screws. I think that instead of choosing one over the other, we need to consider different fixings on their own merits. And I think if you do any functional printing at all, especially if you are designing these things yourself, then a bag of 50 or 100 or maybe more trilobular screws, about 3.5 times 10, 3.5 times 12, will, if you can't, then specialist plastic ones will do. It is definitely worth the small investment to get some kind of plastic-specific screws. And don't forget, these are incredibly easy to use. All you have to do is add holes to the part, and you can do that even in the slicer. And you can use modifiers to change the number of walls and any other properties that you want for the screw holes. Anyway, let me know as usual in the comments what you think. Make sure you subscribe if you haven't. I'll stick links in the description for stuff I used. I will see you next time for the CC2 review. Thank you for watching.